Welcome back, everyone. Thanks for joining us at the Algebraic Combinatorics online workshop, otherwise known as ACOW. Today is our last day of talks for this workshop, but we are wondering what the future will hold for this YouTube channel. So if you can, please subscribe to our YouTube channel, and if there are more talks in the future, you will find out about them. It is my great pleasure to introduce Victor Reiner from the University of Minnesota. He's going to be talking about Whitney numbers for poset cones. Take it away, Vic.
Okay.
Take two is that we're thanking everyone for having organized the workshop and the semester. And I'm going to tell you about Whitney numbers for poset cones. And this is some joint work with one of my PhD students, Galen Dorpalen-Barry, and also Jang Kim from Korea. I don't think I'll try to pronounce your university, Jangsu. So what I'm going to be telling you about is something that's generalizing Stirling numbers of the first kind. So when I say Whitney numbers, I always will be meaning Whitney numbers of the first kind. And so I'll start by reminding you of 4 formulas for the Stirling numbers of the first kind. And then I'll explain what are Whitney numbers for hyperplane arrangements, and then what I mean by Whitney numbers for cones within hyperplane arrangements. And then when we look at type A, hyperplane arrangements, and their cones, we're really looking at posets. So we'll get a notion of Whitney numbers of the first kind for posets. And then I'm going to tell you about a generalization of the 4 formulas for the Stirling numbers of the first kind that arose. That's the plan. So let me start with Signless Stirling numbers of the first kind, the CNKs. And most of the formulas that I'm going to be talking about can actually be found in Enumerative Combinatorics Volume 1, Chapter 1, Section 3. But this formula, the one that I'm going to use to start in defining the Signless Stirling numbers of the first kind, you actually have to go into Chapter 3, Section 10. I'm sorry about that. But you'll see later why this is the one that I'm describing first. So the Signless Stirling numbers of the first kind, CNK, one way to think about them is the coefficients in this polynomial, which is essentially the characteristic polynomial for the partition lattice. It's just an unsigned version of the characteristic polynomial. You might call it the Poincare polynomial for the partition lattice. You sum over all set partitions pi of the numbers 1 through n, and here I've drawn pi 3, the set partition lattice. And what you do is you let the t variable keep track of how many blocks they have, and that's essentially their rank within the set partition lattice. But the coefficient that you put in front is the absolute value of the Möbius function from the bottom set partition, the one that's the discrete partition where everyone's in a singleton block, up to that element. And so here I've drawn the set partition lattice. I've labeled in green these Möbius function values from the bottom up to an element. So from the bottom to itself, it's +1. From the bottom to any atom, it's -1. So there's 3 of them that are -1. And from the bottom to the top, in this case, it's +2. And the signless Stirling number of the first kind is what you get when you aggregate the absolute values along a rank here. So this +2 gives me the 2 that you see here, that's C31. The -1, -1, -1 totals to -3, and then we get rid of the sign, where we know that these numbers will alternate in sign anyway as you go up the ranks, plus, minus, plus. So the absolute value is just getting rid of some useless extra information. And then at the bottom, we just have a +1, and so the absolute value is +1, and that's this signless Stirling number of the third kind. So I'll be interested in this sequence of numbers, 1, 3, 2. Okay? So that's one way to define them. And maybe the more familiar way to define them for most people, and the first way that you would think of it, is signless Stirling number CNK is just the number of permutations in the symmetric group Sn having k cycles. So this generating function, the sum CNKT to the k, is just the generating function for permutations according to the number of cycles. Sic of sigma is the number of cycles of sigma. And one way to see the relationship between these two different versions of the generating function is the map from S3, the permutation group, that takes a permutation written in its cycle notation to just the set partition, which correspond to the cycles. So you turn each cycle into a block in the set partition. That map has the property that when you fix a set partition, the number of pre-images will be the absolute value of the Mobius function from the bottom up to that set partition. So for most of these set partitions, the number of pre-images is 1, but for example, for the set partition, which is the indiscrete partition in which all the elements are in a single block, there are 2 pre-images. And that's not hard to see. We know explicit formulas from EC1, chapter 3, section 10. For each set partition, the Mobius function value from the bottom to the top is explicitly a product of all of the blocks of the size of the block minus 1 factorial. And that's how many ways you can create a permutation that cyclically permutes things within those blocks. Not hard to say. Okay, so that's our second formula for the Stirling numbers of the first kind. Another way to rethink the Stirling numbers of the first kind is using a different statistic on the symmetric group. Instead of looking at permutations and counting them according to their number of cycles, you could count them according to the number of left to right maxima. So you think of the permutation as a sequence of the numbers 1 through n in a certain order. And a left to right maxima means you're reading from left to right. And each time the value is the biggest one you've seen so far, then that's a left to right maxima. And so there's a beautiful bijection due to Dominique Foata he called his first fundamental transformation that bijects the symmetric group, here it's S3 to the symmetric group, and which takes the number of cycles to the number of left to right maxima. All you do is you take your permutation and writing it in its cycle notation is ambiguous. First of all, within a cycle, you don't know where to start writing the elements in the cycle. Well, he says, make it unambiguous by putting the largest element at the beginning of the cycle. Like in this cycle with a 3 and a 1, the largest is the 3, so you put it first. And then in what order do you write down the cycles? You look at those largest elements, here they're in purple, and make sure that they are in increasing order. That's how you choose in what order to write down which cycle. So here's the cycles written in that standard form, and then Foata's transformation just forgets where the parentheses are. You erase the parentheses, and now those elements that were at the beginning of the cycles, these purple elements, have turned into the left to right maxima. So it's very easy to see how to go backward, and why it's a bijection is if you have a permutation, you read it as a sequence. Every time there's a left to right maxima, you should put a left parenthesis before it, and then that determines where the right parentheses should go. There's something in the chat. I can't see the chat. Here we go. Chat. Oh,
I didn't think this to you.
Okay, good. And one more formula. So you might just be thinking about the signless Stirling numbers of the first kind in terms of their generating function. You can explicitly write down this generating function. It has a nice factored product form, and there are many, many proofs of this. Again, I think this you can read in chapter 1, section 1.3. But in our case, those coefficients, the 1, 3, 2 in front of the generating function, give this factored form, t times t plus 1 times t plus 2 up to t plus n minus 1. Okay, so those are the 4 formulas that we're going to be looking at. Any questions so far?
I don't think so.
I think we're good, yeah.
Good. All right, so, right, those are the 4 formulas. And let me also say, where are we heading with them? We are going to be trying to generalize the symmetric group, which we can think of as just all linear extensions of the numbers 1 through n, to the linear extensions of any poset, any finite poset. And so for the symmetric group, it's the linear extensions of the anti-chain poset, in which there are no order relations. And so we'll generalize the 4 formulas, And the first three of them, actually, there is a very reasonable generalization to all finite posets. The last one, only I know of a generalization to disjoint unions of chains, but it's really beautiful, and I love the fact that it connects to a different bit of Dominique Foata's work, which is in his thesis, the theory of intercalation product and factorization, unique factorization of multiset permutations. So hope we'll get there to tell you about that. Okay. So how are we going to be generalizing these Stirling numbers of the first kind to posets? Well, we start by talking about Whitney numbers of the first kind, and let's start with it for arrangements. So there's a famous result of first Winder and then Tom Zaslavsky in his thesis that says for an arrangement of hyperplanes in a real Euclidean space, so here I've drawn it inside R2, and here I've got three hyperplanes, which are just three lines. They will cut up the space into chambers. So you take the hyperplanes out of the space, remove them, look at the connected components, and those are called chambers. I think of them as open chambers. And we want to count them. In this picture, there are 6 of them, these 6 pizza slices, if you like. And one way to count them, according to Winder and Zaslavsky, is you sum over the intersection lattice, the lattice of intersection subspaces X that you get by intersecting the hyperplanes. And so these intersection spaces X can be of any dimension. You order them by inclusion, or rather by reverse inclusion, turns out to be consistent with what we were doing before. And you just sum up the absolute value of the Mobius function values from the bottom of that poset, which will be the whole Euclidean space V, up to the intersection space X. You sum up those numbers and you'll get the number of chambers. And here's an example. For this arrangement that I drew, here is the intersection lattice. The whole vector space V, which was R2, is at the bottom. Oh, and I guess in this example, this is a picture in R2, but it's a projection from R3 of the hyperplanes where x1 equals x2, the first and second coordinates are equal, x2 equals x3 is this hyperplane, and then x1 equals x3 is this hyperplane, projected from R3 to R2. Here's the intersection lattice. You have the R2 at the bottom, you have the 3 hyperplanes at this rank, and then the origin, which is at the middle, is the intersection of all 3 hyperplanes. That's at the top, okay? And you can see that this picture is the same as the partition lattice, pi3. It's isomorphic, which we'll talk about. So the Whitney numbers we already computed. The Stirling numbers of the first kind are 1, 3, 2, summing up the Mobius function values across the rank with taking the absolute value. And they sum up the 2 plus 3 plus 1 to the number of chambers. That's the Winder-Zaslavsky theorem. What's perhaps less well known is a later theorem of Zaslavsky from a couple years later in his paper. I think it's called a Combinatorial Theory of Topological Dissections, maybe combinatorial analysis of topological dissections. He proved that essentially the same formula generalizes and is just as easy to prove when you want to count not all of the chambers in an arrangement, but the chambers that are inside an open cone. I should have emphasized the word open on this slide. So I'm going to pick some of the hyperplanes, look at the open half space on one side of the hyperplane, and more of such things, and intersect them. Pick a bunch of hyperplanes and intersect their open half spaces to get a cone that I'm calling calligraphic K. And if I only want to count the number of chambers of the original arrangement that are inside that cone, you just do something very similar. So here I've drawn 2 cones. Here's a cone inside the arrangement we had before that has 3 chambers. Here's a cone that has 2 chambers. And the way you count their chambers inside the cone is you just only sum up the Mobius function values with absolute value for certain intersection subspaces X. Namely, you pick the intersection subspaces X that actually do cut through that open cone, that intersect the open cone in something. So in this case, the cone is actually an open half space, and the only intersection spaces which intersect it are the full R2, that's the V at the bottom, And then these two hyperplanes, the x2 equals x3 hyperplane, that's here. The x1 equals x2 hyperplane, that's here. What you get, and we call this the interior intersection lattice, L int of k, it's an order ideal within the original intersection lattice. And so, in fact, these elements have the same Möbius function value because their lower interval looks exactly the same. It's just only certain of the subspaces contribute. You still sum across the ranks, add up these Whitney numbers for the cone, so it's a 2 plus a 1 in this case, gives us 3 chambers. And that's why we got the 3 chambers here. Or for this cone, in this example, you only have the full space as an interior intersection, or the hyperplane x1 equals x2 is an interior intersection. And so you only sum up their absolute value of the Möbius function values. And you get these Whitney numbers for this cone, 1 and 1, which add to the number of chambers inside the cone is 2. Any questions there?
No.
Good. Okay, so we have a notion of Whitney numbers for cones, and they will be non-negative integers that sum up to the number of chambers in the cone. So how do we get to posets? Well, we pass through a dictionary that, you know, it's getting to be pretty old now. Back in, I would say, the 70s and 80s and 90s, this was kind of a cool idea. I, in some sense, learned this first from Stanley's theory of p-partitions, you know, from his thesis. Ira Gessel's paper in 1983, where he introduced QSIM, has a remark at the end about talking about inequalities for other reflection groups that are similar to p-partition cones. And then there's papers by Anders Brunner and Michelle Wax from the late 1980s and early 90s, where they very explicitly talk about this correspondence between convex subsets and cones in reflection groups and linear extensions and posets, linear extensions and posets. So the dictionary goes like this. It says, if your arrangement is the type AN-1 reflection arrangement, or the braid arrangement, whose hyperplanes are all hyperplanes of the form xi equals xj, then permutations in Sn, we can think of them as indexing the chambers, and I'll show you a picture on the next slide. Basically, the permutation tells you what's the ordering of the coordinates within a chamber. Posets on the numbers 1 through n correspond to cones, namely the poset P corresponds to the cone K sub P, where you intersect the half spaces xi less than xj for I less than j in the poset. And then linear extensions of the poset P correspond to the chambers of the arrangement, those permutation index chambers, where that permutation was a linear extension of P. And the intersection lattice for the braid arrangement is the set partition lattice, pi n. So let's take a look at an example. Here, I've drawn the A2 or symmetric group S3 braid arrangement, and it has the 3 hyperplanes that we were talking about before, x1 equals x3, x1 equals x2, x2 equals x3. But now I've oriented them to say on which side is x1 less than x2 or x2 less than x3. And you see what happens is those connected components are defined by what's the ordering of the coordinates, x2, x3, x1, you know, in increasing order of the coordinates, x2 less than x3 less than x1. So chambers are permutations. And the intersection subspaces, well, when you intersect hyperplanes, which are where xi equals xj and xj equals xk, you get xi equals xj equals xk. The point is the coordinates get grouped together into blocks where the coordinates are equal, and the ordering by refinement is reverse inclusion of the subspaces. So the partition lattice is the intersection lattice. And then the cones, well, if I only impose this half space condition that x2 is less than x3, I think of that as coming from the poset in which 1 is less than 3 and the 2 coordinate is unrelated. Or this cone, I intersected the hyperplanes where x1 is less than x3, excuse me, the half space where x1 is less than x3 and where x2 is less than x3. And so that cone corresponds to the poset in which 1 is less than 3 and 2 is less than 3. No other order relations. And the chambers inside this cone correspond to those permutations which are linear extensions of this poset. The whole picture is not hard to see once it's pointed out to you. It's pretty easy to check that all these things work. Good, so posets correspond to cones in the braid arrangement. And now if we think about what Zaslavsky's second theorem there was telling us, this says, whenever we have a poset on the numbers 1 through n, if we define these Whitney numbers for its cone, I'm just calling it CK of P, but it's really the Whitney number of the first kind signless for the cone corresponding to P. And so that's the sum of these Möbius function values. Question in the chat. Tuators, if I don't put the sign on the Möbius function value, I could recover the sign anyway, because in the partition lattice and in any of these intersection lattice, the sign alternates. It goes plus, minus, plus, minus. It's not extra information, and I want to add up non-negative numbers to get the number of chambers. Good question. Okay, so I'm defining the signless Whitney numbers of the first kind for the poset to be the ones for the cone. I sum up these Möbius function values over the intersection subspaces, the interior intersections at the kth rank. And Zaslavsky's theorem is going to tell me those non-negative integers refine the number of linear extensions. Here I've written number of lin_x of P just to remind myself what this number is. This was what Stanley was calling E of P in his talk, the extensions, linear extensions of P, same number. So we get this non-negative integer refinement for any poset. And what I want to emphasize before I answer some chat questions is that refinement of the number of linear extensions will depend upon the poset only up to isomorphism and not on the labeling of the poset. It's really geometric because when you relabel the poset, you're just applying a symmetry in the braid arrangement, one of the elements of the reflection group or the symmetric group, and it takes it to an isomorphic cone with isomorphic intersection, interior intersection poset. All the numbers will be the same. Let me see what's going on in the chat. Oh yeah, Sam has an answer about signs. Yeah, bounded regions are interesting in this story, Sam, and actually Galen, Dorpalen-Barry, and Theo Duropoulos and Jose Bastidas Olaya actually have some work about that. So yeah, you should ask them about it. Andrea is asking, don't you get a problem in this sign equals rank when you have more connected components? No, Andrea, you don't. The interior intersection poset really is an order ideal within the intersection lattice. It's really true that if you keep this, it's not really a ranked poset anymore, but it's sort of ranked from the bottom. The signs still alternate. Anyway, let me move on. Okay, so we get this isomorphism invariant decomposition of the number of linear extensions of the poset. And so let's try to understand it. Let's try to move the page. Okay, yeah. And so in the formulas that we had, they were about the anti-chain poset. And let's see how these formulas generalize. So the first one was the one in which I had used roughly speaking, the Poincare polynomial or the characteristic polynomial of the partition lattice to define the signless Stirling numbers. So here, if we just identify which subset of the set partition lattice are the appropriate set partitions that remain when you take a poset cone, which ones are the interior intersections, they correspond to the set partitions which we call P transverse for the poset P. And what does P transverse mean? It means that if you've, here's an example of a poset, this poset, which is a disjoint union of two chains. I've drawn some P transverse set partitions on its elements. And what P transverse insists on is that if you quotient, if you glue together the elements of the poset that are the same block, the quotient pre-poset, it'll only be a quasi-poset because now some things have been set equal. It will never set equal two elements that were strictly less than each other before, where there was a strict order relation. So, for example, this P transverse partition, it glues together the 1 and the 2. It makes it a 12 down here, less than 3, less than 4. But notice, 1 is still less than 4, 2 is less than 4, 1 is less than 3, and so on. 1 is less than 4. excuse me, the point is you never squashed any of the covering relations, any of the strict order relations in the poset when you quotiented by pi. Here's another p-transverse set partition. It glues together the 1 and the 4 to make this quotient pre-poset, but that one does not squash any of the former order relations, any of the cover relations 1 less than 3 or 2 less than 4. Here's 2 non-examples, some not p-transverse set partitions. This one squashes the order relation 1, 3 because 1 and 3 are in a block. And this one's more subtle for why it's not transverse. It puts the 1 and 4 together, and then it puts the 2 and the 3 together. But then when you take the transitive closure, it means that all of the numbers have been put in the same block in the quotient pre-poset. So that's not transverse. Okay, and so this is not hard to prove. I call it a proposition because, you know, it's one of the easier things in our paper. It's just checking what does it mean to have an interior intersection for poset cones. It's a relatively easy exercise. Slightly more interesting is when you excuse me, this is just the example for this poset here, the disjoint union of 2 chains. I've drawn all of the p-transverse set partitions. So here is a picture of that order ideal within the set partition lattice. And these are the interior intersections drawn as set partitions, or they're the p-transverse partitions. And these are our Whitney numbers. 1, 4, and 1 gives us 6, which should be the number of linear extensions. And indeed, there are 4 choose 2 linear extensions for this poset, which is a disjoint union of 2 chains. Okay. Now, slightly more interesting is the second formula, the one that said the Stirling numbers of the first kind were keeping track of permutations according to the number of cycles. What you can do is say, these Whitney numbers for the poset are keeping track of p-transverse permutations, not set partitions, but there's a notion of p-transverse permutation. And all it is you insist that the permutation have its cycle partition. Think of its cycles as giving you a set partition and ask that they be p-transverse. And then it's easy to see from the previous result that the Whitney numbers of the first kind for the poset are going to be keeping track of these p-transverse permutations according to their number of cycles. This again comes from our formula for the Möbius function of set partition being this product of the number of blocks minus 1 factorial. That happens to be the number of permutations that have that set partition as its cycle partition. And so that's really the same thing that related the formulas before relates them now. I like this formula because it's summing over, you know, objects and the permutations and counting them according to their number of cycles. I just wish that the summation was over linear extensions. And so in that sense, we wanted more formulas. Okay, and here, in fact, these are all the p-transverse permutations. In this case, because my poset had width 2, so it turns out that in that case, there is only one p-transverse permutation for each p-transverse set partition. So the fiber sizes are all 1. And so this picture looks very much like the picture of the p-transverse set partition. There's only one way to orient the cycles. And now we're counting these p-transverse permutations according to their number of cycles, essentially. Okay. What about the formula in terms of left-to-right maxima? So this is something that we were looking for a while, and then eventually Jang was the cleverness behind this bijection. There's a beautiful bijection that generalizes Foata's first fundamental transformation. It takes the p-transverse permutations to linear extensions, which is what we want. And it has the property that it takes the number of cycles in the permutation to some statistics that we called LR max of P, the P left-to-right maxima of the permutation. I'm not going to describe this bijection. It uses breaking up the poset into layers. You look at anti-chain of the minimal elements and then remove those. There's some cleverness involved, but I just want to say that it beautifully generalizes Foata's transformation, you know, breaking the thing into the cycles, writing it in a standard form, and erasing parentheses. So Good. So that formula has an analog. And then this last formula, the one that's the product formula, as I said, this one only will generalize to the disjoint unions of chains. So let me introduce a notation for the sizes of the chains. Let me call the size of the chains in a disjoint union A1, A2 up to AL. So that one that we looked at before was P sub 2, 2, and the chains are of size 2 and 2. We have in the chat. Oh, yeah, that's a great, Greta asks, what happens when we do that bijection for standard Young tableau? And yeah, I don't know the answer, Greta. We have not carefully tried to look at what you get. That's great. Francois asked, do you have refinements in which you count by cycle types, giving Polya cycle index series analogs of your identities? Have not thought about that, Francois. Yeah, good question. I do not know. Good. Okay. So for disjoint unions of chains, what I'm claiming is the generalization of this product formula for the Stirling number generating function is let's keep track of with a monomial what the size of the chains, sizes of the chains are, x1 to the a1, x2 to the a2, etc. And then put in front of that this Whitney number generating function for that disjoint union of chains. And then I claim it has this nice rational function expression that's 1 over 1 minus a sum in which you have something that looks similar to the factored product formula that we began with, and then some elementary symmetric functions in the x1 through xl in front. And I claim that if you try to extract the coefficient for x1 of the first, x2 of the first, up to xn of the first, that would be the case where the disjoint unions of chains just gives you an anti-chain. You can deduce from this generating function that generating function that we began with. Let me see what happened here in the chat. Oh, yeah, Twitterus, I didn't understand your question, McMahon. Maybe you can clarify that later. And Brennan asks, is there a proof of the product formula using a variant of Solomon's work on superspace differential forms? Well, our product formula, I see, because you're right, Brennan, the original product formula is certainly related. That's a great question. I don't know the answer. Good question, Brennan. Okay, so where does this come from? More chat question.
Vic, it might work better if you let Petra interrupt you if and only if the question is pressing.
Sounds good. You filter, Petra. Okay, so where does this come from? This is the more interesting part than just actually getting this generating function. It comes from Foata's thesis. So Foata, in this great thesis, he did many things, but in particular, he defined something called the intercalation product of multiset permutations. And he didn't just define it, he proved that there's a unique factorization for multiset permutations into prime cycles up to a certain lack of uniqueness coming from commutativity. So let me just give you the rough idea of what's going on here. This is the multiset permutation of 2 1s, 3 2s, 2 3s, and 3 4s. So the A1, A2, A3, 4 is 2, 3, 2, 3. This is what it will correspond to. The A's give you the multiplicities of the numbers. And here on top, you see them in increasing order in a 2-line notation. On the bottom, you see them in some multiset permutation order, 2, 4, 4, 3, 1, 2, 1, etc. But the content should be the same for 2s, 3s, and 4s. Foata tells us that we can factor this into what he calls an intercalation product. That's what this symbol is, where still on the tops, you see the numbers in increasing order. And the way you take 2 multiset permutations and intercalate them is you write the numbers on top in increasing order, but underneath the ones, everybody should be in the same order that you see it on the right side. So here it's 1, 1, 2, 4. Okay, it's still about below the 1 1s, you see 2, 4. Here you see below the 2s, I see a 4, a 3, and a 1. So over there below the 2s, it's 4, 3, 1. Below the 3s, I see a 2 here and a 1 here. So below the 3s here, I see 2 and 1. Below the 4s, it was 3 and then 4, 2. So here it's 3, 4, 2. That's how you intercalate. What he shows is that product, which may seem a little bit silly at first, It has a beautiful, unique factorization for every multiset permutation into pieces that are prime, that can't be factored further. And the prime pieces look like permutation cycles. This is like 2 goes to 4, 4 goes to 3, 3 goes to 2. That's like a standard cycle in a permutation. This factorization is unique, except that you can see for the intercalation product, when your contents are disjoint, the 2 cycles commute for the intercalation product. That's the only ambiguity in the way you write it in terms of prime cycles. And then what we'll care about is the statistic that we'll call p-cyc, or for prime cycles, 4 prime cycles for this multiset permutation, because there were 4 there. Okay, so he develops this. It takes some work. And then the point is, when you've got a disjoint union of chains, if the chains are sizes 2, 3, 2, 3, well, you can take a linear extension and read it as a multiset permutation that has 2 1s, 3 2s, 2 3s, and 3 4s. All you do is color the chains, relabel them, say this chain with 8, 9, 10 is the 4s. When you see the 8, 9, 10, you replace them with 4s. And you can go backwards. You take the 4s wherever you see them, you replace them with 8, 9, and 10 left to right, the usual standardization. So there's an easy bijection between linear extensions of disjoint unions of chains and multiset permutations. And then you reinterpret Foata's main theorem. And what you can think about it is he's really giving us, for linear extensions of disjoint unions of chains into we identify those with multiset permutations. And his bijection, his factorization, bijects them with those things I was calling the transverse permutations, the things whose cycle sizes interpreted the Whitney numbers. So you can reinterpret his theory as giving a bijection between the linear extensions and the transverse permutations for the poset, taking his number of prime cycles to just number of cycles. So he lets us reinterpret the Whitney numbers of the first kind for these posets as counting his multiset permutations according to how many prime cycles they had. And then, oh, here's an example for this poset. Here's the linear extensions reinterpreted as multiset permutations, their prime cycle decompositions, and you group them according to how many of their prime cycles. One of them had 4, 4 of them had 3, one of them had 2, and there's our 1, 4, 1 that adds up to 6, just thought of in Foata's way. And so I love Foata's theory. Yes.
Could we pause with one question?
Yes.
From Richard Stanley. So
Yes.
in your formula, in this, so if you instead extract the coefficient of t to the n, so the formula on 3 pages back, the symmetric function.
Let me go back. Whoop.
So then you get a symmetric function. Can you say anything about that? If you extract the
coefficient, yeah, right. So in some sense, that's in Foata's theory, we are fixing the number of prime cycles. I haven't thought about it, Richard, and I don't know whether we can say anything about that symmetric function. Yeah, good question. So let me just come back to what I think is one of the most interesting questions, coming out of our paper is there some theory of intercalation product and a factorization theory for all posets, not just disjoint unions of chains, that would give us a statistic like this Foata's number of prime cycles on the linear extensions and reinterpret the Whitney numbers? We've thought about it a bit. We didn't quite see how to do it, but I would really love to see it. And I think it would be a beautiful thing if it existed. So, thank you for your attention, and thanks to the organizers for having ACAL.
Thank you, Vic. It was wonderful. And I think if there's more questions, maybe better
yes,
take them.
maybe, no, not really.
I wanted to ask a question.
Okay.
Is there some version of a cone for complex arrangements, or a complexification of the real cones in a way that this sort of statistics that you have is Poincare polynomial, the Betty numbers of the complement?
It's a great question, Theo, and I've thought about it a little bit, and I failed to come up with something there. Yeah. In fact, I think Volkmar Velker, when Galen and I were telling him about this early on, he had a similar idea. You might actually want to check with Volkmar to see if he made more progress than I did, because I got stumped on trying to provide topology, complex topology for the cones. It's a great idea.
Thanks.
Okay, Vic, I have a question.
Yeah.
For your last question or conjecture, beside the ones that you studied in the posets, do you have further evidence?
You know, let's see. Not really, to address. I mean, one thing is that there are plenty of posets for which we have nice formulas for the number of linear extensions, you know, beyond the disjoint unions of chains. For example, forests. There's the Knuth's hook-flying formula for forests, and Bierner and Wax did beautiful results about the Madge generating function for those. Even for those, I don't currently have a nice formula for these Whitney numbers. And I think even for those, if we could understand that, it would help toward that intercalation product question.
Thank you.
So maybe I have a question then.
Yeah.
So can you, are there any unimodality log concavity properties of these sequences? Have you looked into that?
You know, Peter, when Galen gave a poster at a conference and Philip Jang asked about real rootedness, because obviously the Stirling numbers of the first kind, the generating function is real rooted. It turns out they're not always real rooted, even for some of the disjoint unions of chains. On the other hand, for width 2 posets, we don't yet have any counterexamples to them being real rooted, even more strongly than unimodal or log concave. But there's not a humongous amount of evidence for the width 2 posets having that property. So that's about as far as we got, actually.
Do you have counterexamples to log concavity?
I don't think so.
So yeah, so I see that Eleni is raising her hand.
Okay, hello. So I have a very simple question. So does the Zaslavsky theorem for the interior intersection lattice hold for affine arrangements as well?
Yeah, and
I mean, if
really
somehow yes, if somehow they create a cone and we have some regions within the cone, can we still count the regions in the same way?
Yeah, but one thing is, Eleni, already an affine arrangement you could think about as a cone within a central arrangement, because
okay, yes, taking one dimension further.
That's right. That's right.
Okay, okay, yes. So it's the same, yes. Okay,
yeah.
Thank you.
It's no more general.
Okay. Mm-hmm.
So I don't think there's any more questions right now.
Very good.
Great, then thanks again, Vic. Thanks to all the speakers of today and to all the speakers of our 2-week event.